in. And so, good evening. The session is being recorded, and Linda's doing some behind-the-scenes work for us there, so we can do this. Now, as always, I'm reminding you that the VCM folks are supposed to be watching the net videos, and the net folks are supposed to be watching the VCM videos because we're covering complementary material in both. You're getting a richer course that way. And one of the videos that is online, and if you've seen it, that's good, because it's about Doppler effect and such. And that's, we talk about a lot of the physics in that video. But what Linda's going to be firing up is a PDF, so it's not going to be slides, but actually this might even work better than chopping it into slides, because I'm going to follow the Doppler effect here, at least for a while. So Linda, we're just going to be scrolling along with that document for a while.
All right, I'm still trying to get it downloaded, so give me 1 second.
You found it though?
Yeah, it's labeled Chapter 19, right?
Yep, it is.
Okay.
But, okay, that's kind of what I had in mind. This is I'll say a few more things though while Linda's getting this done. This is the 14th week, and this is a short week. So we're getting shorter and shorter. We'll have 2 full weeks after this, and we'll have tonight of VCM things. There will be online lectures, but we're in very good shape to finish what we're supposed to, and that, so we're in very good shape. Very soon I'm going to be, and the VCM class, of course, is going to be having the final. I know we already discussed that. I'm going to be reminding you of that. And if anybody has accommodations, everybody's going to get accommodated, but you're getting accommodated on the front end, not the back end, because there is no back end after the term finishes. So anyway, so soon this will be there. So this is the 14th week. Let's see, I talked about that. And maybe that's everything. Linda, maybe one thing we could do at the outset when you get that positioned, and I'll let you figure out how to do it. Let's do a poll and see how people are doing about
Okay.
Dimpy asked, when is LSA14 due? I think Linda said that was due the Tuesday after we get back. Is that what you said, Linda?
I believe so.
Yes.
Yeah, December 1st.
Yeah. Or whatever the Tuesday we get back is. And we have, and actually I was planning on positioning another, okay, so now Linda's posted this, so how are you? And so you should vote. No, Dimpy, I think there are other LSAs after that. There is an LSA 15 already. I think there will be a 16 dealing with the Doppler effect as well. I guess.
All right, that PDF is just about done.
Okay, great. Okay, so that question then was answered. Good, good. Okay, and so now let's see, what did I want to say else? Oh, yeah, most people were doing okay. I think maybe one person was doing great. That's good. One person was struggling. You know how to fix that. We're available to help you fix that. Linda is available quite a bit, and I have office hours. I in fact have office hours immediately after this class. I've been having some of you guys coming, and Tom Topol is available, so there's a lot of help. Okay, and there's some good chat things there. People are answering some questions, but there is a 15. There is going to be a 16 too. And the 16 has to do with the Doppler effect. Now, Linda, is that, and if that is, that's fine. Is that as big as that can show up, or can you do some magic with that?
So I think they can individually zoom in.
Okay.
But I have no way to control it for everyone.
All right, so here we go. Okay, so anyway, this is talking then about Yes, we can. Josh says we can, so good for you. And Linda, does that mean I can do it too?
You can.
Okay, can you tell me what to do just quickly?
If you have a touch screen, then you can just kind of zoom in like you would on your phone.
I don't have a touch screen, so I can't do it.
Okay.
That's okay. Don't worry about it. That's fine.
I'm sure there's a way to do it. I just don't know off the top of my head.
Yeah, and I mean, that's fine. Okay.
There should be a little piece of paper with a magnifying glass on the left-hand side, I believe.
Yes, there is.
Okay, you should be able to zoom in using that.
So I'll make bigger, bigger, bigger. Okay, that's good. Now, and then this scrolls down. Yeah, this is great. Okay, so here we go. All right, so I'm just going to be reading with you then, but this is maybe a less scientific thing, okay? So have you ever stood on the street corner when a motorcycle passes and you start hearing the engine seem to increase in frequency or pitch as it approaches and then decrease? That's the Doppler shift. Okay, so the Doppler shift is all about relative motion, thank you, Linda, relative motion between the source and the receiver, and it creates a frequency change. So the frequency of the sound changes as you get closer and closer together and further apart. And the sound doesn't change when the distance is a constant. And this is used to determine about blood circulation and blood speed. So we'll go to the next page, and here we go. So the Doppler shift is a low frequency that rides on top of the much higher transducer frequency. So you see, here's what's going to happen. The transducer might have a frequency of 5 megahertz or 2 megahertz, some kind of megahertz, but the Doppler shift is a very low frequency that rides on top of that transducer frequency, and we'll talk about how that is. And the process of extracting the low Doppler frequency from the transducer carrier frequency is called demodulation. And that's something that I did a lot of when I was working in telecom. We talked about modulating signals and demodulating signals. So for example, during a Doppler exam, sound with a frequency of 5 megahertz is transmitted from the transducer and reflects off moving red blood cells. The frequency reflected is 5 megahertz and then 3,000 hertz more. It's 5,003,000 hertz. The Doppler shift, or change in the frequency, is the plus 300 hertz. The shift is positive because the reflected sound has a higher frequency than the transmitted sound. When the Doppler shift is positive, blood cells, it's my dog. Actually, it's not my dog, it's my daughter's dogs. Okay. But I can't mute them, so there we go. The shift is positive because they'll eventually stop because the reflected sound has that might be Amazon delivering something, because the reflected sound has a higher frequency than the transmitted sound. When the Doppler shift is positive, blood cells are traveling towards the transducer. And so the Doppler shift in hertz is equal to the reflected frequency minus the transmitted frequency. And then there's a note there in purple. Transducer frequencies of 2 megahertz to 10 megahertz are used to perform clinical Doppler exams. However, Doppler shifts are much lower, and their range from 20 hertz, just 20 hertz, to 20,000 hertz, and are in the range of audible sound. Now, I don't know if you listened to the video that I posted, but I encourage you to do that because actually you can hear some Doppler sound, and if they turn up the volume, if they turn up the speakers, and you're doing a Doppler study, you can actually hear it. And I bet a very good ultrasound technician can just listen to the Doppler shifts, and they know what's going on just from listening to it. Okay, but and someday you guys will be that good. And then let's go see if I go down. Yes, I do. All right, so here's how it happens. Creation of a frequency shift. I'm sorry, Linda, I'm going to let you point. I was doing that, and that doesn't make sense having two hands up there. Doppler shifts are created when transmitted sound waves strike moving red blood cells. So in this picture on the right-hand side, then, what we have is a blue transducer. So you see the blue transducer is sending a signal there, that's the black signal, and it goes. Now this signal hits the red blood cells. You see the red blood cells are rushing directly towards the transducer, and so it reflects off, and the red signal comes back from them, and the transducer can pick up and read the red signal. So this says blood cells moving towards a transducer reflect sound with a higher frequency. Okay, and I guess we said all that about positive Doppler shifts. So let's go to the next page then. Maybe I can do that without making Linda do that. She's probably got her hands full pointing, I think. Okay, when blood cells move away from the transducer, the shift is negative. And again, let's look at the figure. So you got this transducer, the blue transducer, that is blasting a black signal after the red cells who are running away. Now, eventually, that catches up to the red blood cells, and it does send a signal back. But this signal, since it's running away, and again, that's something you understand from the Doppler shift, that's going to be a lower frequency. So this is going to be called a negative Doppler shift. So blood cells moving away from the transducer reflect sound with a lower frequency. Okay. And so I guess the words over here, I think we already talked about that. So the Doppler frequencies indicate velocity, not speed. You see it's negative if it's moving away. So it's really telling you if it's moving away or moving towards you. Now speed, you know this from your earlier physics, is purely a magnitude, and that's a distance that it moves in 1 second. And so the speed is recorded. Now it is coming towards you or going away, but the speed is simply recorded then in terms of units of centimeters per second or any other distance divided by time. Velocity is defined by a magnitude and a direction. You guys all know that. That's a vector. And so think of velocity as an arrow, and the length of the arrow is the magnitude, and the angle at which the arrow points is the direction. Okay. And here's an example. And you guys know all this stuff really well already, but we'll just plow through it quickly. So an automobile is traveling from New York to Florida at a rate of 50 miles per hour. Speed is 50 miles per hour. Speed is magnitude. But the velocity is 50 miles per hour to the south, because that's a magnitude and a direction. Okay, now this is not the same Doppler equation that I showed you in the book and in the video. And there's a reason it's not, is because some things in ultrasound are somewhat simpler. And so, and Josh, I think you and I had a discussion during some office hours one time, and I told you that if I'm at the top of my game, and sometimes I am, Linda's probably thinking not often, but sometimes I am at the top of my game. And if I'm at the top of my game, what I'll do is I'll cut out this equation and I'll paste it in there with those others in your grace notes. But this is a Doppler equation, but this Doppler equation just works for ultrasound. Okay, so this says that the Doppler shift, which is in hertz, because it's a difference in frequency, is equal to 2. Now, you might wonder, where the hell does the 2 come from? And I will explain that later. But there is a 2 in this equation. You might say, well, there's not an equation 2 in the book. Well, yeah, but if you think through it, there should be a 2 there. And it doesn't mean the book is wrong. It just means the book's talking about it differently. So this is 2 times the velocity of the blood. And by the way, that velocity of the blood is either going to be positive or negative, because that goes into the dark area. Linda, can you read that question that somebody typed there?
Yes. LSA14 and 15 will be up and ready as soon as I have free time again.
Oh, okay.
So probably this weekend.
The reason I interrupted to deal with that was because I thought it might be a question about the Doppler shift equation. Okay, so anyway, it is 2 times the velocity of the blood. Now, velocity is going to be positive or negative depending on if it's going towards the transducer or away from the transducer. So you see, you can have a negative Doppler shift over there, but that gets reflected in the velocity of the blood. Okay, and then that's being multiplied by the transducer frequency. That's the next factor. And the transducer frequency is going to be something like 5 megahertz or 2 megahertz or something like that. And then it's going to be times, and what Linda's going to point to next in that numerator is cosine of theta. Now we're going to talk about what the angle is. You might say, wow, there wasn't a cosine theta in that video. But if you listen to the video, I said, notice that in some of the pictures that I show you in the video, the transducer is at an angle towards the blood flow. And if the angle isn't 0, then you have to do a vector kind of thing, and that's where the cosine of theta comes from. And then that's being divided by the propagation speed, and the propagation speed is the propagation speed of sound in soft tissue. And you should almost have that memorized these days, okay? So again, just to recite this equation again, you don't have to memorize it. It's going to be there, but you have to know how to use it. So the Doppler shift is equal to 2 times the velocity of the blood times the transducer frequency times cosine of theta, where theta is the angle between the flow of the blood and the transducer, divided by the propagation speed of sound in whatever tissue you're in. And the propagation speed of sound, is at 1540 meters per second. 1540 meters per second. Okay, so that's there. Now, you might say, well, gee, do I have to worry about units? Yes, you really do. So you see that transducer frequency probably will come in megahertz. The velocity of the blood is not going to be that. The Doppler shift is probably going to be in hertz. And the propagation speed depends on what kind of units you're using there. So you do have to be concerned about units, and you have to make sure that your units become hertz when you work through that. And by the way, an equation, what I'm probably going to ask you is, I'm going to tell you something about the Doppler shift and the other elements, and I'll say, how fast is the blood flowing and in what direction? That kind of question. Now we're going to talk about this equation some more, but everybody realize that that is an important equation, and that's the reason I asked Linda to cover this first, because I already gave you the other video, and we're going to go back and do some other things later, but I wanted to at least get through this equation tonight. Okay? Very good. Okay, so now we go into a little bit of question and answer. So the first question is, what is the relationship between the velocity of blood and the Doppler shift? The Doppler shift is directly related to the velocity of the blood cells. The faster the velocity, the greater the Doppler frequency. And so here's an example. Assume that a Doppler study is performed and the Doppler shift is 8 kilohertz when the blood velocity is 2 meters per second. If the blood velocity were to slow to 1 meter per second, the Doppler shift, and you see 1 meter per second is you're halving that, and so that means the Doppler shift would be reduced to 4 kilohertz. When the velocity is halved, the Doppler shift is halved. And Linda, I'm going to, let's see, I think I have control of this maybe. Yeah, so I'm going up here. And you see that's because it's here in the numerator. So you see if you double or change the velocity, you get the corresponding change in there because they're directly proportional. So that's good. Now we come to the important question of why is there a 2 in the Doppler equation? Now, and you can work problems using the equation that I showed you in the video, the physics equations, but you have to be kind of clever. And here, I'm not going to say they dumb it down, but they make the equation easier for to use. So there is a 2 there, and here's why. The 2 actually represents the fact that there are actually 2 Doppler shifts during an ultrasound exam. The first shift occurs when the sound wave from the transducer strikes the moving blood cells. So the moving blood cells reception of the sound wave is in itself sufficient to create a Doppler shift. Okay, but now what we're going to do is we're going to the next page, and I guess I will do that. After the sound wave strikes the blood cells, reflections return to the transducer. And the second Doppler shift results from the transducer's reception of the sound wave from the moving blood cells. So you see that 2 belongs there, and it would come up if you use the equations that I showed you before, but you realized that they had to add in that way. Okay, so now we're moving down. If the Doppler shift is measured with units of frequency, how do ultrasound systems report blood velocity? And that you see at the top that this is talking about hertz, which is frequency, versus centimeters per second. So how do you do that? Well, modern ultrasound systems actually report the frequency differences between the received and transmitted waves. However, the Doppler equation is programmed into the ultrasound system's computer. The computer uses the frequency information and the Doppler equation to calculate and display the frequency. And in fact, you all know that the velocity is equal to wavelength over frequency, so you could even do that calculation yourself. But in other words, the actual data that is measured is in frequency in units of hertz, but the calculation is done and you will get units of meters per second. This approach is appealing in clinical settings because knowledge that the velocity of the blood in an artery is 0.4 meters per second has more clinical relevance than knowing that the Doppler shift is 3 kilohertz. Okay, and this over here shows the spectrum with the Doppler shift scale in kilohertz on the left side, and that's the red arrows, and the velocity scale in meters per second is on the right side. And that's a display that you could be looking at, or someone could read the report from that. Okay, the y axis represents the Doppler shift, and the x-axis going along there represents time. Okay, very good. Okay, let's talk just a little bit about this. A few more questions. What is the relationship between the transmitted frequency and the Doppler shift? Well, mathematically, the Doppler shift is directly related to the frequency. That means the higher the frequency, the more the Doppler shift. In fact, Linda, I'm going to go back to that equation. There it is at the top. You see, the higher the transducer frequency, here it's in the numerator, and the higher the Doppler shift. Okay, so they are directly proportional. Now I'm going to go back to wherever the heck I was. In other words, if the transducer's frequency is doubled, the measured Doppler shift will also be doubled. Now, by the way, that's the kind of question they ask on your certification exams. They don't give you numerical problems like I do, just because those would be hard to grade. But I think it's important you know how to do that and not just do multiple choice questions. But that's the kind of question. So here's an example. A Doppler study is performed with a 2 megahertz transducer, and the Doppler shift is 3 kilohertz. If the identical study is performed with a 4 megahertz transducer, the Doppler shift will be 6, because what really happens is that you see going from 2 megahertz to 3 megahertz is an increase of 50%. So an increase of 50% on 4 is going to be 2 and takes you to 6. Okay, so that is good. Let's scroll down here and see what else is here. Process of calculating velocities from measured Doppler shifts is not obvious to the sonographer because the calculated velocities will be identical regardless of the transducer frequency. because the calculation of velocity, the frequency is netted out. So the Doppler shift is measured in hertz. It's directly related to velocity and directly related to transducer frequency. Okay, here we go. And we got just a little bit more. Okay, now this is the sound beam direction versus the flow direction. And Linda, I think I'm going to ask you a question. Okay, it will be a question you know the answer to, so that's going to be really great. And Linda knows enough math, she can do this without a calculator, but you guys will have calculators, so that's going to be fine. The measurement of the Doppler frequency depends on the relationship between the direction of the blood flow and the direction in which the sound wave propagates. This is about direction, not speed. So you see, when the blood cells are moving parallel to the sound beam, and that's in this first picture right here. So the blood is either running away from the transducer sound beam or it's running to the transducer sound beam. So you get it's going there. But that is parallel, and it's parallel because the angle between the two is what, Linda? Degrees.
0.
Yes. And Linda knows that the cosine of 0 is?
1.
Yes. Okay. Now you can pound that in your calculator if you don't know that, but if you're doing a lot of trigonometry, you might know that anyway. And Linda, what is the cosine of 90 degrees?
That would be 0.
That would be 0. Now, Linda, so think about if you aim the transducer, and Linda and I did not rehearse this, but I think she'll be able to do this. So here in the picture you're pointing at there, Linda, the angle between the blood flow and the other thing is 0. Show us where the transducer would be if it were perpendicular. Yeah. And you see the cosine of 90 degrees is 0. So you see, if you're there, you're not going to get any Doppler shift because I'm moving all the way back. You see the cosine of theta is up here. So if that's 0, you don't get any Doppler shift and you're SOL, okay? So that's like a real bad place to put the transducer. And in fact, that might be the kind of question that they could ask on a certification exam too. Hey, if you put the transducer perpendicular to the blood flow, you know, what happens with the Doppler study or something? Well, the Doppler study is totally worthless. And you might say, well, I am going to be an ace ultrasound person, so I'm always going to have an angle of 0. You can't do that because if you can't generally do that because if you were doing that, you'd be sitting there right inside the blood vessel, and you kind of can't do that. So that's hard to do. Okay, let's go back to this. When the blood cells are moving, maybe I read that already, did I? When the blood cells are moving parallel to the sound beam, the entire velocity is measured. The entire velocity is measured because it is 1, as Linda said. Okay, so it's 100% accurate. I actually don't like the way this guy says this. I mean, I think the measurement is accurate no matter what you do, but he's just saying that you have that cosine theta. However, when an angle exists between the direction of the blood flow and the sound beam, next paragraph, the internal velocity is less than the true velocity. And here's a picture of that. Now, this one is not perpendicular, it's at an angle, but this is kind of realistic because you say, well, that's the best I can do is to stick it there. And so when there's an angle, it measures something less than that. But you see, by putting the cosine theta in there, you deal with that. And so you actually do get the velocity of the blood from solving that. And you might think, well, yeah, Jim, but you're always going to pretend on assessment or something like that this is 0. And I will tell you, no, I won't. I might say, oh, it's 60 degrees or something. And so you would have to incorporate that into your thing. So I guess we really talked about that. Now here it talks about the cosine of theta, and they start giving you, they don't talk about cosines as fancy as we do. And there's a list of angles and stuff. But you guys know how to do this because we've studied trig in here. And so it talks about if theta is reduced by half, the measure of the Doppler shift will be reduced by half because it is in the numerator. Okay, and here's the picture where they show you, the cosine things. And as Linda said, If it's 0, it's 1, and if it's 90, it's 0, and so on and so forth. And I think all the rest of these things we know. So use that equation. And I think we've really talked about all that. The cosine of 60, if you looked up that, that would be a half. And so that's what that's saying there. Okay, very good. And Linda, I think that might be the end of this. Yeah. Now, this book goes on and on and on. It talks about all kinds of fancy Doppler things, and you can do bidirectional Doppler studies and things like that, although you have to have a very fancy transducer to do that, because we talked about transducer normally blast one way and then it listens to come back the other, but it's possible to buy a fancy one, and you can measure things continuously, things like this. We could go on and on and on about the Doppler shift, but you get the general idea. And Linda, I think historically I've almost always had a problem on the final exam about the Doppler shift, and I don't think
that is correct.
Yeah, and I don't think I'm going to do anything different this year. So I think you want to understand that. But we're going to suspend this discussion right here, Linda, of this. And I think this is going to be in the thing. And if you want to read some of this, but this is all the further we're going to go in the lecture, and that's up to page 311. So we really didn't even talk about this. And this gets really into, you know, fancier and fancier stuff. And when you guys get into the ultrasound program, you'll learn more about this, and this will be great. And you'll be able to do all these studies. But that's, I'm choosing to stop there in chapter 19. I'm going to pause for a minute and ask if there are questions out there other than when a low stakes assessment is due. Okay, so that's good. So Linda, now can we shut this one down, and let's go back to the PowerPoints then.
You got it.
Thanks, Linda.
And you'll probably need to zoom out.
Okay, probably. Let me do some of that. Okay, and I don't know. There we go. Now, this is about describing sound waves. And we already covered this because I gave you lectures about waves. You might say, oh, I didn't understand all of that. Well, maybe that's okay because we're covering it again, but we're covering it from an ultrasound book and just seeing how they do it. And there's different kinds of questions that they ask. It's the same content though. And so those lectures were good that we had, you know, talking about these things in general wave motion, but this is the ultrasound piece of it. And so you want to understand both. And we talked about parameters. So parameters then describe features of a sound wave. The values of 7 parameters are required to completely characterize a sound wave. And the 7 parameters are shown over there in that little blue box. And so we can talk about the period. We can talk about the frequency. We can talk about the amplitude. We can talk about the power and the intensity. And we can also talk about the wavelength, and we can talk about the speed. So you see, if we're talking about sound wave, we can talk about all of those things. And you're supposed to understand what all of those things mean from a physics point of view, but we're going to talk about those. Now, those actually are organized into groups in this, and later on we'll look at this picture again, and we'll talk about why they're there. But you see, some of these things the ultrasound technician has control of. Other things you don't have control of. Some things have to do with the medium you're going through. Some things have to do with the medium and things you control, and other things are totally out of your control. And I don't know if I did 4 things there or not, but anyway, we'll talk about all of those things. And that's, in fact, I think what the next paragraph says. It is not enough to learn the meaning of the parameters. You must know which units are used to report values of the parameters. For example, the units associated with age can be any unit of time. It could be years, it could be seconds, minutes, or decades. The units associated with height could be inches, feet, meters, or miles. Sometimes parameters have synonyms, and it's useful to know the names of all of these, know all of the names of these parameters. And so, let's see. It says at the end of your studies, actually at the end of this lecture, you will understand why it's arranged this way, and that helps you to organize and recall the material effectively. I don't really get that, but maybe that's true. Whoever wrote this book thinks that's true. Okay, so that takes care of these. And so everybody understand what we're doing. We're talking about these things just in the context of ultrasound only now. Everything we talked about previously was true. This is just in terms of ultrasound. So here we go. We're going to talk about the period. And let's just, yeah, Linda, I think the yellow is a good place to start. I really don't know where. You know what I think the yellow is? I think they're saying if you take note cards, you might want to do that. So maybe, tell you what, let's do not the yellow, but then we'll do the yellow in a bit. So let's go over to the thing. And Linda, I actually don't know which way is good here. If you know whether the parameter is determined by this, you have to know whether the parameter is determined by the sound source. That's something you adjust on your transducer, or the medium, which is the soft tissue you're going through. You will be able to understand how these parameters relate to physical principles of ultrasound physics. Okay, so here we go. The source. The source of a sound wave is the ultrasound system and transducer. The quality or level of some of the parameters are established by the ultrasound system. The sonographer can adjust the level of some of these parameters where others cannot be changed by the ultrasound technician. Other parameters are determined by the tissue through which the sound is traveling. The tissue is also called the medium. It is important to know whether the sonographer has the ability to change the value of a parameter while using a particular transducer. And otherwise, is there a knob, a control, or a switch on the system that will allow you to alter the parameter's magnitude? Lastly, you should know the typical values for the parameters. In clinical medicine, it is helpful to know the normal values. In ultrasound physics, we should know the common values. And the reason it's normal is like if somebody takes your temperature in degrees Fahrenheit, they know if you're running a fever or not. And so that's the kind of thing that's happening here. Okay, so let's go through then, and let's just talk about these notes then. And I guess the notes really are complementary to that, but anyway, I guess he's thinking these are good like note cards. I'm not sure. Okay, so anyway, the period. And you remember that period was time. So period is the time it takes a wave to vibrate a single cycle. So that's time per cycle. That's the time from the start of one cycle to the start of the next cycle. Okay. And Linda's showing you over there. So the wave's period is identified by the red arrow. Now, the red arrow there is saying a length of time, though, in this picture. And in fact, this is a picture that maybe is very useful, but it also really could be very confusing, because Linda is saying the red arrow is the period, that is the time it takes. But also, well, we'll talk about that again, and we'll use the same figure. Well, that's time. Okay, that's good. Never mind. I was going to make a different point, but I shouldn't do that. So period is reported in units of time, and it might be microseconds, seconds, hours, or days. Now, I've got to tell you, in ultrasound, it's not going to be days, it's not going to be hours, it's not going to be seconds. It's probably going to be, well, it could be, it's probably going to be microseconds, just because you're talking about sound waves and you're talking about very short distances. Typical values of the period here, they're talking about that. And so that's the third thing down there. And so typical values of a period ranges from 0.06 to 0.5 microseconds. And if you wrote those in scientific notation or general notation, you'd see you would have 10 to the negative values there. Or writing it in decimal points, but then you have to count the zeros and stuff like that. Or you can just use microseconds. And you, as an ultrasound technician, should know what all these mean and be able to change from one to the other. I was talking with the students the other day in office hours, And this student said, hey, why don't you give us a problem where we do a calculation in, we just do a calculation and I have to use scientific notation in the calculation. And I told the student, I said, you know, I might do that, but I'll probably do that in the context of a problem, because if you were calculating that Doppler shift or the velocity, you'd have to be doing that big time, because these things would be in megahertz and so on and so forth. Okay, going down, period is determined by the sound source only. So you see, it's the sound source only, that is the transducer, determines the period, not by the medium. But is it adjustable? And the answer is no. The sonographer, that's the ultrasound technician, cannot change the period while using a basic ultrasound system with a particular transducer. Now, you could have different transducers that you use and things like that, but a transducer is firing at a certain period. So anyway, that's the answer to that question. Okay. I don't know, Linda, should I be pausing here or just keep going for questions?
I think you can keep going.
Okay. If you guys got questions, please ask. Okay, so here we go. We're going to be talking about frequency now. Now, frequency is different than period. Frequency is the number of particular events that occur in a specific duration of time. For example, the frequency of presidential elections, how timely is that in the United States, is 25 times per century, 2.5 times per decade, and once every 4 years. It also happens every leap year, I guess. In diagnostic ultrasound, the frequency of wave is described as the number of cycles that occur in 1 second. So you see, I a lot of times just call it cycles per second because I'm teaching an ultrasound course, and that's really the way a math guy probably would talk about this as well. But it could be events. I mean, you could talk about the frequency of presidential elections, except that would be like social studies or political science or something like that. Okay, frequency, we'll talk about units of frequency, and you know this already, but frequency is reported in units of per second. Now, that says units of per second. That means this is reciprocal seconds. You see, it's 1 over a second, and 1 over a second is called a hertz, or Hz. Hertz is another way of saying per second. And so you see different things here. So you could have a 1 hertz, you could have 1 kilohertz, or you could have a megahertz, which would be times 10 to the 6th. Okay, in medical imaging, frequency usually is between 2 megahertz and 5 megahertz. No, I think that's 15, actually. I think I cut that off. But that's 15 megahertz, okay? I think that's not used as much, but anyway. Let's see what we have on the other side here. Okay, the frequency is determined by, the frequency of sound is determined by the sound source only, not the medium through which the sound is traveling. Is this adjustable? No. And the reason it is because the ultrasound technician is not in charge of the medium it's going through. That's wherever they pointed you to do the study. And so this is not adjustable, so you cannot change the frequency while using a basic ultrasound system and a transducer. I suppose if you get something fancy enough, you can do everything. Actually, you could never do this because, well, let's see, the frequency, oh, it's not by the medium. It's not, excuse me, I think I read that wrong. Frequency of a sound is determined by the sound source only. It is, but the transducer, unless you have a very fancy transducer or a whole bunch of different wands, it's not the medium. It has nothing to do with that. And so here you see in the pictures down here then, you see in figure 3.3, in this illustration, the wave's frequency is 4 per second, or 4 hertz. You see that time going from the 0 to over there is 1 second, and it goes through 4 cycles there. So that's 4 hertz. The next one is 8 cycles that occur in 4 seconds, the one below that. So there are 8 cycles that occur in 4 seconds. So the frequency is 8 over 4, or 2 hertz. Okay. Josh has a comment. Let's go back to that page because that might be where his question is. Go ahead, Josh.
Yeah, real quick. Is the cycle? That's just another term. Another term for that is oscillation, correct?
Yeah, and Linda, you want to give that a go?
Yeah, so really we're just looking at how long it takes to go through one complete wave. So very similar to the period almost.
Okay. Thank you.
Okay, very good. Okay, so we'll go to the next. And how did ultrasound get its name? And you might say, well, who cares? Well, I got to tell you, I've seen some sample, I've never taken a certification exam, but I've looked at sample certification exam questions, and there actually is a question that I have seen, multiple choice question about this. What is ultrasound? Okay, so I mean, you may someday take a certification exam. I hope you do, actually, and hope you do well on it. But anyway, this might be a question there. So sound is classified based on the ability for humans to hear it. So if the frequency of a sound wave is less than 20 hertz, it is below the threshold of human hearing and cannot be heard. Now, your dog and my daughter's dogs, who visited us in this class the other day, or not the other day, a few minutes ago, actually, maybe could hear something below 20 hertz, but a human really can't. And so that sound is inaudible. And sound waves with frequencies there are called infrasonic or infrasound. Now, humans can hear sounds with frequencies between 20 hertz and 20,000 hertz, or that's also could be 20 kilohertz. Now, this sound is called audible. Back when we used to have analog telephony, and I actually go back to that era, we always engineered the copper cables to transmit 4 kilohertz. And you can actually distinguish voices if it is 4 kilohertz. So it's very tolerable, and so since that was acceptable, we did that. And so it used to be I could tell when my mom called me, I would, I could recognize her voice, and if my sister called me, I could recognize her voice. If my sister were to call me or my brother calls me, I know who it is because I can hear the voice. But now things are digital, and so things are, somewhat different. And in fact, the digital, the 4 kilohertz of analog bandwidth is digitized into 64 kilobits. But anyway, if you're between 20 hertz and 20,000 hertz, it's audible. People can hear it. Now, you might be saying, yeah, but I went in to buy a stereo system. The guy was telling me that this has a frequency response of 28 kilohertz. And he said, I really should get that because it's 28 kilohertz. Well, he or she is blowing smoke at you because your ears aren't good enough to hear that last 8,000 hertz. Now, it's there, but you just really can't hear it. Anyway, sounds with frequency so high that humans cannot hear them are called ultrasound. Ultrasound is any frequency that is higher than 20 kilohertz. Now, we did talk last time in our lecture about people hunting for ships, and they were using 50 kilohertz. So technically that was ultrasound, but the ultrasound you guys are using tends to be megahertz, not this. But if the question says, oh, for something to be ultrasound, what does it have to be? The answer is it has to be higher than 20,000 hertz or 20 kilohertz. Okay. Why is frequency important? Because it affects the penetration. And we talked about the penetration, how deep it goes. We were talking about the range equation the other day, and image quality. Okay. And what's the relationship between frequency and period? Period and frequency are inversely related to each other. As frequency increases, period decreases. As frequency decreases, period increases. And those are the kinds of questions they ask on the certification exam. And this thing up here, this is just a summary of the things I talked about, with a great deal of detail earlier. Okay, I want to get to some questions pretty soon, but not yet. Okay. Oh, if one of those parameters, either frequency or period, remains constant, the other one is unchanged. So here it says period and frequency have an even more special relationship. It's called the reciprocals of each other. So the period times the frequency is always 1. Okay. Then there's a picture here, and what it says is reciprocal relationship between period and frequency. The frequency of the wave is 8 hertz. And you can see it's 8 hertz because you go through 8 cycles per second. And Josh, going back to your question, if you can look at this and say, yes, I see that that's 8 cycles per second, then you're good with that whole thing, okay? But so the frequency of the wave is 8 hertz. That's 8 cycles per second. But the period is going to be the time between those, and so it's going to be 1/8 of a second. And so in this little example, then a wave takes 1/8 of a second to vibrate up and down. Thus, the period is 1/8, but the frequency is 8 per second, or 8 cycles per second. And remember to use complementary units, seconds and hertz, and milliseconds and kilohertz. To tell you the truth, I don't get that so much, but I don't know. They're both powers. The first was 10 to the 0. The second one is either 10 to the -3 or 10 to the 3. Okay, so anyway, that is that. And we are going to be doing some questions soon, Linda, but not yet. So frequency is reported in hertz, and it really doesn't mean cycles per second. In ultrasound, it usually does, but it could be, elections per second or events per second or things like that. If a person has a heart rate of 1 hertz, that's 1 heartbeat per second. They're either a very remarkable athlete or they're really sick, I think. But anyway, in our case, it almost always means cycles per second. Aha, Linda, finally some questions. Okay. And I think maybe I'll do this. And Linda, why don't you, if you don't mind, lead this discussion. And what's going to happen is we've got 5 questions there. They can make them bigger and things like that. But we're going to do poll. And Linda, I think you like to do these one at a time.
Yeah, sounds good.
Okay, so Linda's going to make up a poll. You'll respond. And you're doing question 1. I guess I'll read it for you. What is the period of the Earth's rotation around the sun? And you see the answers there. So pick an answer and please play. And Linda, I'll let you figure out whenever you think we're done. And you can circle an answer, and then we'll go ahead to the next question. Okay, let's go to the next question. I guess I'm reading these for you. A top is spinning on a table. What is the period of the spinning top? And again, I really encourage you to weigh in on these. No one's grading you. But it helps you actually to think about these things. Okay, Linda's found an answer. That's good. Let's move on to the next one. Which of the following waves is infrasonic? This is good practice for your certification questions. And maybe it's useful, but I'm not going to ask you multiple choice questions because I don't want to do that. Okay, Linda found an answer to that. And she's marking it. That's good. This is identify the wave that is ultrasonic. Okay. Well, Linda hasn't answered it yet, so you guys are still thinking, I guess.
I'm hoping a couple more people will play.
Okay. It's really useful to play. There's no risk. It's almost like going to a casino and somebody gave you money to gamble with. I mean, it's not a gamble, though, so. That's one of the things that's an important skill in teaching, is being able to wait till someone answers. Okay, we have an answer there. Last question on this page. Which of these waves is, oh, it's a compound question. Which of these waves is ultrasonic and most useful in diagnostic sonography? Okay, Linda, if you can kind of memorize those answers. The only reason I'm asking you to memorize them is because there might, I mean, if the group got any of them wrong, then we should probably talk about that for sure. Otherwise, we'll field, questions. So the Earth moves in one cycle around the sun in a year. That's D. The only one that has the correct units of time is this. By the way, that is a goofy kind of question that sometimes they have on these certification exams. They didn't give you enough information to figure out anything except that the period has to be time, and only one of those measurements is time. And so but you guys did good on that. Let's see, a wave with a frequency less than 20 hertz cannot be heard, and that's infrasound. This is ultrasound, because it's this one. And here, okay, yeah, this
5 was the only one they got wrong.
Yeah, okay, thank you. Yeah, so although A, B, and D are all ultrasonic, only answer B falls within the typical range of frequencies used in diagnostic ultrasound. See, this is not megahertz, that's kilohertz. That's like in fact, that's almost like a broadband cable TV system. Let's see, you guys aren't especially interested in this probably, but in terms of an analog frequency video, is like 6 megahertz. So this would be a whole bunch of video channels. 4 megahertz was the correct answer. And this was only, 200 kilohertz. And so that's, yeah, that's 0.2 megahertz. Okay, so let's go to the next one then. Okay, some more problems for you to do. I guess we're doing these one at a time too, Linda. Okay, so identify. Oh, wait, Abby has a question, and Abby's question might be back on the other one, so I'm going back to the other slide. Yeah, Abby, what's up?
No, sorry, I clicked that. I thought it was the pull button.
Oh, okay. All right, so we will go to this one then. Okay, so this is identify the waves that are inaudible. And more than one answer may be correct. Oh, wow, that's a tricky one. Okay. I guess you get to vote multiple times, and it's going to be kind of hard to grit. Well, I don't know. Wow. And Linda will make a call in a bit, and then we'll go on. I am watching the time for you guys, so don't worry, we're in good shape.
So I'm assuming all the fluctuating numbers mean A, B, and D are all answers.
Okay, just, I mean, figure out how to encode that, and then we can move on.
Yeah, I got people hopping around like crazy, so that's what I'm going with.
All right, good enough. Number 7, which of the following waves has the longest period? We're getting some good participation here, Linda. I don't have the thing up.
Yeah, a little bit.
Okay, good.
About half the class is participating.
Okay, again, I would encourage you to do all this because when you take a certification test, you have to be filling them out to get credit, because if you don't fill it out, they'll count it wrong for sure.
Just waiting on a tiebreaker.
Okay. If it's still tied, just circle both, and we'll see if either one of them is right.
All right.
I shouldn't do that. It's like I'm overruling you. That's not what I want to do. Are we ready for number 8?
Yep. I already started the poll.
Okay, good. Of the 4 waves, which whose periods are listed, which has the highest frequency? Okay. Okay, excellent. Of the 4 waves whose frequencies are listed below, which has the shortest period? Got to read these problems carefully, I think. Okay, excellent. Of the 4 waves whose periods are listed below, which has the lowest frequency?
You guys are really good at making ties tonight.
Someone wrote period up there. I don't know if that's a question or just a comment of some kind.
All right, I'm just circling all 3 of them then.
All right, so here we go. Let's see how we did. And Linda, kind of give me some kind of a sense of, okay, A, B, and D, I think that was correct there.
Yes, it was.
This should have been C as number 7.
7, they marked A and B.
Okay, so let's talk about that. The wave with a frequency of 8 hertz has the largest period. Period and frequency have an inverse relationship. Thus, the wave with the lowest frequency has the largest period. And so that is going to be C. See, that was only 6 hertz, and this was 1 kilohertz. Okay. Sydney has a comment. Go ahead.
Can you kind of explain the frequency and the period? Like, I don't understand how you got either of those answers. Like, how I don't understand how C is the answer.
Okay, let me do that. And again, I know what time it is, so don't worry. I know what time it is. F is a reciprocal of this. So if you're doing this problem and you know the period, is going to be the biggest number, okay, is going to give you the smallest frequency. And, you know, and also it's like this, T equals 1 over F. I don't know, Linda, you want to say something any more about this, or did I
So
do it?
frequency and period are inversely related, meaning as one gets bigger, the other one gets smaller. So if we're trying to figure out which one has the longest period, then we're talking about which one has the shortest frequency. So that's why we're picking the smallest number, which is C.
Okay, okay. Okay. I understand that. Thank you.
Yeah, no
All
problem.
right, good. Okay, let's see. This one should have been B. This one is A. And this one was C. And they're kind of explained there in words, but they all pretty much follow from this, this relationship. Okay, Linda, I'm just going to the next slide to see what it is. I do know what time it is. Now you all know, okay, now next time we're going to talk in this class about amplitude, power, and intensity. But even though we don't have class again this week, I'm going to be doing math. And so there might be videos and things like that. So, you know, watch for them, and in between eating a Thanksgiving meal or something like that, you watch for them. There is no class in here on Thursday, and there's no more office hours this week until Monday. And Linda, you have no more things until Monday as well, right?
That is correct.
Okay. So you guys be safe. That's important, and we'll pick it up here, but watch, because there's going to be more videos. Time is precious. Each day must count. Do the math. It'll make you strong. Take care, everybody. Happy Thanksgiving.
Have a great
Happy
Thanksgiving,
Linda,
everyone.
thank you. And, are you going to be able to upload that or something?